Tooth, here with another Ask an Astronomer, which of course we have our astronomer, Marley. How's it going, Marley?
I'm doing well, Michael. How are you today?
I'm doing wonderful. We have a very special show today. Of course, we've got some news, some things that are happening out there in the solar system, but we're also going to be talking about gravitational waves. And if we're going to talk about gravitational waves, we are bringing in our favorite guest that we have had on not this show, but on Cosmic Nights and some other shows. And that is someone who's the detector operator at LIGO that detected gravitational waves, and that is Corey Gray. Hey, Corey, how's it going?
Hey, how's it going, Michael and Marley? Thanks for the invite.
Yeah, this is going to be really fun. So, Corey, you're a special guest, and we're going to ask you some questions, and our guests out there that are watching, they maybe have some questions for you about gravitational waves, how LIGO works. So get in on the chat and ask Marley, ask Corey questions about all those things. And then, of course, we're going to talk about Indigenous knowledge because it is National Indigenous Month. And Corey, you are also from the Siksika Nation. So that is really cool. We're going to talk about some of that a little bit later at the end of the show. But let's start us off, Marley. What's going up? What's going on in space right now? You're muted, Marley.
There we go. So what's going on in space right now? You may remember last week from when I was talking about how, wrong screen, we were going to go to Venus. Well, again, Take 3, the European Space Agency just announced that they will also be sending an orbiter to Venus. The Envision mission has been given the go-ahead and selected to go. This mission will be looking at the inner core to the upper atmosphere of Venus, and they're really looking at why did Earth and Venus evolve so differently. So on this orbiter, there will be 5 different instruments and 1 experiment, looking at core, mantle structure, signs of active and past geological processes, looking for past existence of oceans. And the launch period is a bit in the future. It won't open up until May of 2032, but they are very excited that it's been selected. ESA is running the main mission, but NASA will be contributing what's called VENSAR, which is a synthetic aperture radar to be able to make high resolution measurements of the planet's surface features.
Oh, that's so cool. Venus was so neglected, a few months ago, we were sort of like, it's a really bright star up there in the sky. And then all of a sudden we've got 1, 2, 3 missions now planned to go. This is amazing.
No, it's really, giving Mars a run for its money at the moment. Very, becoming very exciting once again. But Venus, I think, has always been interesting to look at because it started so similar to Earth, they think, right? It's called Earth's evil twin or Earth's twin, and that we're this pretty close to the same size, pretty close, might be made of the same stuff. But what happened to make Venus so inhospitable is really a big question. So it's always been interesting, but always very hard to explore there.
Corey, what do you ever think about Venus when you're down there in LIGO? Like when you're dealing with gravitational waves. We're going to get to gravitational waves, but do the planets, are they like they're small fries for you down there at LIGO?
I guess so. I've just been so busy. I mean, I heard some of the news about this last week, and I mean, it's interesting. I'm definitely interested in things that are astronomy related. And especially like some of the moons for like Jupiter and Saturn. Those are the ones that I'm also interested in. So it's always, my ears perk up a little bit when I hear about our solar system, for sure.
Well, speaking of moons of the gas giants, we might have something special for you, Corey.
Yeah, great segue. Juno went by Jupiter's moon Ganymede recently, just last week, and sent back some really awesome photographs. So the last time we were this close was in May of 2000 when the Galileo spacecraft made its approach. And so Juno took these photos and took some measurements looking at the composition of this moon. Ganymede has a really interesting ice shell around it, which scientists are very excited by. And looking at the composition of its upper atmosphere, which is like not an atmosphere like we have, but it's quite thin, but still very interesting to look at. And as well, it got some pretty sweet photos. These are 2 official ones that have been released. And the excitement about the ice shell is that it has some darker and some lighter regions. So the lighter regions may be pure ice, whereas the darker regions may be quote unquote dirty ice. And the interest in the dirty ice is, well, what is in there to make it so dirty? Like what possible elements and the compositions could be in there. And so the measurements will look at the composition, how it varies with depth. And, they may be really nice pictures, but it also complements future missions. NASA has plans to go back to Jupiter's moons, as does the European Space Agency, has a whole mission dedicated to it called the JUICY mission, standing for Jupiter Icy Moons Explorer. Yeah, so it'll be a whole thing coming up. So the full photo on the right of the screen is taken with a green filter on the Juno cam. The image resolution is about 1 kilometer per pixel. So I really suggest looking at this photo from NASA's press release on your own computer. There's some great detail that you can zoom in on. And versions of the same image will be coming down in the next couple of days, next few weeks, that will utilize the blue and red filters. And so the people at NASA will overlay all those filters, the green, the blue, and the red, to get a color portrait of the moon. The close-up photo on the left is from the Stellar Reference Unit, which is the navigation camera that Juno uses. And this provided a simple black and white photo of the side of the moon opposite of the sun. And so the light illuminating the moon isn't from the sun itself, but it's the sun that's been scattered off of Jupiter. And the image resolution in this picture is about 600 to 900 meters per pixel. And you can check out the JunoCam website for raw images that are being put on and images that have been processed by the members of the public, images like these. So all of these images were taken from raw Juno data from the JunoCam and then processed largely by Kevin M. Gill, who does some great work. And so check out the link there to see some of these pictures. They're really phenomenal with a lot of different surface features on this moon.
Yeah, absolutely. Kevin Gill is one of the goats, as the kids say, when it comes to processing NASA photos. If you can look into our YouTube archive, you'll see an interview that I did with Kevin, all about his work on processing these images. Which he does work for JPL, but as like a computer engineer, and he purely does this as a hobby. But that's why what this cam was set up to be. It's like citizen science. Anyone can go onto this site, and if you want to learn the skills, there's even some videos that you can learn, pick up a new hobby and learn how to process some of these images. So cool. I have a question for anyone out there watching on YouTube Land, and for you, Corey. Have you ever looked at Jupiter with a telescope? Is this something that you have done at some point in your life?
I believe I have. It wasn't very high resolution. I could at least see the layers or the stripes of the planet, I think. But yeah, I can't remember when that was though. But yeah.
So even if you looked at Jupiter, even with a really simple telescope, you may have seen Ganymede before, because there would be these 4 like what looks like stars, sort of like around Jupiter. And of course, that's exactly what Galileo saw when he first looked at Jupiter. And Ganymede is one of those, right, Marley?
Yeah, one of the Galilean moons. Yeah.
And so we're talking. So Ganymede it's quite a large, right? Like it's almost not quite Earth size, but it's
bigger than Mercury. So it's got a decent size to it. It's a pretty hefty moon. Yeah.
So certainly a place that is very interesting in our solar system, and we haven't really explored it that much. And one final thing about Ganymede, Marley, is that I believe early on, in the exploration of Ganymede was sort of the 4 Galilean moons, because you got Io, Europa, and what's the fourth one? Why am I missing?
I always forget the fourth one too.
The forgotten fourth brother. But Europa and Io sort of get the most love, because Europa's got that really thick ice sheet that might have the under ocean. Io's the active volcanoes. But now what we're seeing, Callisto, that's the 4th moon. It took me a while to get my brain wired there. But now we're seeing that the Ganymede actually potentially has some ice on its surface as well, right?
Yeah, the ice shell has become particularly interesting. Like, what's driving that ice shell? Where did that ice come from is always a big question, how to get there. And possibly the fact that it is a fully differentiated body. So it has like a core and layers and things like that. And it might have an internal ocean that may have more water than Earth's oceans combined. And so looking at that is very interesting.
Awesome. Well, we're certainly going to learn more about that, hopefully from the JUICE mission, one of my favorite named missions that are coming up.
Juicy.
But
Yeah, they really work hard for those acronyms. That's for sure. They really do their work to get them.
That's one of the major things with an acronym is that you have to make it stand for what you are doing, but and also make it fun, right?
Yeah. You have to make it fun.
Speaking of acronyms, let's get to LIGO, which is, see if I can get this right, the Laser Interferometer Gravitational Observatory.
Mostly, yeah, Laser Interferometer Gravitational Wave Observatory.
Gravitational Wave Observatory, almost. Maybe a B minus there.
Yeah, LIGO. So I remember being like, oh, LIGO, it's one spot, but there's actually two parts to LIGO, right? There's the Livingston and the Hanford observatories in LIGO. And there's also this kind of like a sister one, Virgo. So both are giant laser interferometers. LIGO has arms that are 4 kilometers long. Virgo has 3 kilometers. And Corey, is it true that for LIGO being built, they had to take into account the curvature of the Earth when they were building these arms?
Yeah, definitely. They had to, when they surveyed the foundations for the tubes, the beam tubes, we did have to account for that.
Yeah, because the arms have to be totally straight for this to work, right? Yeah.
Yeah, and one thing about your picture that you had, the first picture is one that's actually one I took many years ago. I think
really?
2008. So that was a friend, a colleague rented a small plane, and I invited myself. So I took that photo, a lot of photos, and that one gets used actually a lot ever since our first discovery.
Of the Hanford or the Livingston photo?
The Hanford one.
The Hanford one.
Yep.
Oh, wow. Okay.
I was there just today. I was there just today, and I drove down the beam tube that's at an angle, that's aiming towards about like 10 o'clock. I drove down that today.
Oh, wow. Okay. Were you fixing stuff? Because I know it's undergoing upgrades right now. Both observatories are undergoing upgrades. So were you working on the upgrades to the system?
No, it was just taking photos.
I'm actually curious, Corey, could you just go back to that previous photo, just in terms of like the actual area? So it looks very deserty. So I'm curious, in terms of like when they were choosing locations, like what was it about like these two locations that made them good to build these very large structures? Obviously, you need a lot of space because it kind of looks very deserty.
It is. So, I mean, ideally, the founders of LIGO would have preferred to have different locations closer to Caltech and MIT, which are the universities that run the project. So Southern California or end up in Maine would have been preferred. But I think it's more like a political type thing, or just because this is on government land. The Hanford site is right there, and that's where that detector is on. Luckily, it's seismically quiet, which is very important for our detectors. And then for Louisiana, I think that was definitely more political. I think it was a congressman or a governor who was able to pull strings and make that happen more.
Cool.
Yeah, and their site is a little rougher because it's not as seismically quiet. It's kind of on a sponge because it's a swampy area, and then it's surrounded by trees. So there's always logging that they have to worry about too. So seismic isolation is an important thing for our detectors, especially down there.
Interesting.
Yeah, so in these pictures, top is LIGO, bottom is Virgo. Look very similar. Virgo just has smaller arms, but both are undergoing updates. And recently had to go in, they were starting with observation run 3. If people were watching, you might remember Rachel talking about that back in November when you started up observation 3A. But now we've stopped entirely with observation 3B due to COVID, suspended on March 27th, 2020. It was suspended early, but despite ending early, it was still a huge success. There were more than 5 times more detections than were collectively made during the first 2 observing runs, and culminating with observation run 3B, getting 23 new signals. So is each new signal a gravitational wave detection? Corey, that's what I'm a bit confused on.
23 new signals. I'm just trying to think where that's from. Yeah, so we have, that might be candidates. So I think for O3B, we're still analyzing the data. From what I hear, we're pretty close to announcing and confirming that the candidates are actual detections or discoveries. And so
Okay.
O3A, those ones have all been classified or deemed detection worthy. They're detections. So yeah.
What does the process look like for going through what makes it a candidate to like a full detection?
I've been with the project since 1998. So initial LIGO is what I started with way back in the day. And that's when we ran from about 2002 to 2010, had recorded data off and on during that time. And we made no detections during that time. Back then, we didn't really know how the whole process would go as far as confirming a detection, because in parallel to LIGO's detectors, the experimental work, other physicists were working on solving Einstein's equation. So in parallel, these two different things were going on, because we thought with our data for initial LIGO, we would, the data would be analyzed, but it would take maybe years before it would be confirmed, because Einstein's equations for compact binary systems, which are what we're kind of aiming for, it was hard to solve those equations. And so with supercomputers, even with supercomputers, the thought was that it would take years to analyze the data. But scientists, I think in the UK, were able to solve that for us. And so let's see, I guess, with advanced LIGO, so with O1, as we're recording data live and uploading that data to our supercomputers, they can be analyzed fast enough so that we could usually find out within a couple of minutes whether we have a candidate. And then after that, then it's kind of the analysts, people doing work and looking at the data to confirm whether it's a detection. And that can vary as far as how long that takes to happen.
Okay, so it starts with computers, ends with people figuring it out.
Yeah, and it's becoming more automated. For O3, we make everything public. So anytime we're running and collecting data, everything's analyzed in real time. And if a candidate comes up, you can get an app on your phone and get little dings when we have a candidate. And we give basic information to the public so they could see that. And then we analyze the data afterwards to confirm.
That's cool. And you mentioned like initial LIGO and then advanced LIGO, which also like advanced Virgo, but it turns out is it like every time you get a new update, a new hardware update, you get a new name for the project?
Yeah, so advanced LIGO is covering the three previous observing runs. And then right now we're kind of in the middle of a sort of an upgrade, not a full-on upgrade. It's kind of an addition of kind of a change in the configuration of this picture that we see here. And so this new change in the configuration is called A+, so I guess Advanced LIGO Plus. So it's a small little upgrade that's happening right now. So that's active work. We're pretty busy at the observatories with that work.
Yeah, I saw that's what's happening as well at Virgo. It's like ADV plus is what they've been calling for preparation for observation 4.
Yes.
Go ahead, Michael.
Is there like an official nomenclature, sort of like advanced is sort of like when you upgrade the project, a plus is when you do like a maybe a moderate upgrade. Like what's next? Like advanced Virgo plus. Do we add a super in front of advanced? Super advanced? Does that would be the next upgrade?
Oh gosh, I wish I knew what the upgrade names would be. Yeah, no.
We actually got a question in from Keith, who kind of wants to know a little bit more about the construction of LIGO and how they're able to account for the curvature of the Earth.
I think it's just with the way that we surveyed the foundations, and that the surveyors that we had on site had to be able to make the tube, the beam tube, straight enough so that it would account for the curvature of the Earth. And so, I mean, this is new technology, or this is a new type of observatory. So when would this have been? It would have been maybe 1999 or 2000. And I think Ray Weiss might have actually been at the Hanford site when we shot light down for the first time. And there was suspense because we weren't sure that the light would make it to the end station 4 kilometers away. But yeah, I guess the surveyors did a good job to count for that.
Awesome.
And so I know both LIGO and Virgo are undergoing upgrades. And I found that a lot of the upgrades were mainly, at least at Virgo, were to fight Newtonian noise, which is when like the gravitational flux is from the Earth itself. from like seismic activity, I think is what it was. But I was more interested in the upgrading to the squeezing technique. If you know anything about the quantum squeezing technique at all that's going on, that deals with at like where the mirrors where things reflect the noise that comes from those.
Oh, Marley, I wish, yeah, I knew you might ask that question. That one is a tough one for me. I mean, I've listened to so many talks and it's still hard for me to understand it in a way to explain it. And so I would probably defer. I mean,
No,
so
that makes me feel a lot better because I tried to read a lot too, and I was like, this is going right over my head. I don't know how to explain this.
It's tough. I mean, the squeezer is a new subsystem for the detector that we had in '03. And so for A+, this new upgrade that we're having is basically expanding the squeezer subsystem. And so that's what they're working on now. We're adding a 200-meter long, we call it a filter cavity tube, and we're moving chambers around, these chambers that are around 10,000 pounds. We're moving them around at both ends of this squeezer tube. And so there's so many things that are going on related to squeezing. And so this is definitely some on the forefront of new technology for us.
Yeah, what I gathered from it was that it's to reduce noise, but it will detect the noise so you can subtract it out of the data later to kind of clean it up is the big part. Okay.
I mean, yeah, everything is the name of the game is reducing noise. So, and we've done that in so many, there's different ways that we've done it over the years. And all of that comes down to, so reducing noise increases our sensitivity, which means it increases how far out we can detect sources of gravitational waves. So yeah.
well, Corey and Marley, this is where I jump in and provide the real explanation for this, which is, the cosmos just has allergies. That's what's happening here with the quantum squeezing. Great. Did you have any more updates, Marley and Corey, about? Because I'd love to talk about the translation into Blackfoot.
No, I have nothing else. I'm interested to hear more about the translation as well. I wish LIGO all the best with their updates. There's a lot going on, new mirrors, cleaning things up, whatever that quantum squeezing thing is. So good luck with that.
So Corey, so let's take us back as we've got about 8 minutes here to because I'd love for our audience to learn about this story. The detection was made, you turned on LIGO, and of course this was huge news, revolutionary news. Einstein's theories were proven right, and they underwent tasks to translate the press release into a bunch of languages. And of course, you being there on the team saw it as an opportunity to get your mom involved and translate it into Blackfoot. Maybe tell us a little bit about that story.
So how's the story go? So I'll kind of be selfish and focus on me, just talking about how I joined the project in 1998. And mainly I was a wrench turner, working behind a computer, kind of just working on the detector with my coworkers. And so I was not very outgoing as far as science communication or sharing the work that we do. I mainly wanted to do the work, but I've learned to get better at that over the years. So that's way back in 1998. I was a very shy native kid. But then so yeah, think of that. So 1998, 17 years, no detections made. And then there's that morning, you wake up the next morning and you saw that we made that detection. So, I mean, Marley had a picture of it, but here's the data as well, that first detection. And so that's when everybody's life changed because we're connected to Einstein and we're part of history, and then just all the excitement that happened in September of 2015, and we couldn't say anything about it. We had to analyze the data, and then 5 months later roughly is when we got ready to announce. And a couple of weeks before we announced, there was discussion about the press release and how we wanted to share this with the world. And all of my colleagues are from around the world, so a lot of people volunteered to make translations. And so that's when I kind of volunteered my mom, that's when I came with the idea to do it, to have my mom also work on that, translate one of these scientific documents into an Indigenous language. And so my mom's not a colleague, so I had to get permission first. I had to let them know or asked them if my mom could hear about I actually told my mom, or she already knew, but so it was a top secret, but they said, oh, they're so excited. They said, yes, of course she can do it. So she had 2 weeks and she worked on it. She worked on it with family up in Siksika, which is just an hour east or downriver from Calgary. And so they did it, and they made the translation, and it came out and it was released with all the other translations when we announced in February of 2016. And so I didn't think too much about it because I grew up with listening to my mom speak all the time, mainly on the phone, because I grew up in California, so she'd be talking to her parents, my grandparents up in Canada, almost daily. So I'd always heard our language. I don't know it. And that's because of the residential school system policies, or that's what my mom survived. And so that's why I don't know my language, because of that. And I'm still working on that. And that's the reason why my mom, that's why she realized the importance of our language and preserving it. And I'm still learning the story about it. I mean, so my mom noticed that there were a lot of people not speaking our language. And this was back when she was a kid, like my mom, when she was like 20, like just when she had me and my brother. And so I didn't know that language was a big thing for her when she was my mom back then. But yeah, so it's just kind of cool that to go full circle, to invite my mom to come work with me and then translate the physics of Einstein and astrophysics into Blackfoot. And over the years, after giving tons of talks, I've learned that in my talks, the one part that gets the biggest rise is when I share the work of my mom. And so that's how I've kind of realized how it's kind of an important thing.
Well, it is. It's an incredible story, especially with the knowledge of a language that was almost dying, as you said, because they weren't allowed to use the language when they were put into the residential schools. And we're now learning so much more information of just how impactful those residential schools were to decimating not only the language but the culture. And now it's really important for the work that your mom are doing, and now that you're now realizing this, it's like this realization that we're all having about this impact. I'd love to end us off here, Corey, in thinking of your mom, who's not who's not a physicist, you a physicist, and sort of like almost like bringing together these languages that feel so far apart, and even how she had to get a little creative in coming up with words for black holes and gravitational waves and theory of relativity. I wonder if if you say that you don't know this language, but do you know some of these words that you might be able to share, and maybe we can actually hear some of the language?
Yeah, so there's a few of them that I know that because they translate directly into Blackfoot. So like a word for black hole is the Blackfoot word for black and then hole. And so that's Sigukskia. That's what black hole is. And then there's other types of words where we didn't have a direct translation. And so the one that I know is for gravitational waves. And so that's Epudukspisia och Bigimskaists. And that literally translates to stick together waves. And I think my mom is thinking of electromagnetism or magnets. And so that's where she got that from for that word. And so that's what I love most about the translations, is just hearing the new Blackfoot words that my mom came up with, because it does sound like poetry the way she puts them together. And so, yeah, I'm so proud of her.
That's so wonderful. And this, of course, I think this work is really important. And of course, there's many people around the world that are preserving many of the thousands and thousands of Indigenous languages that have been dying, and trying to preserve them. And now bringing them together with science, it does, I think, give science, this new perspective. And this is why it's important to have so many different languages in the world, because it helps us understand some of these, really grand cosmic concepts, right?
Definitely. Yeah. I think about my mom just being a little kid in Little Washington, a community in Siksika, being, decades later, having a connection to Einstein. And I just think that it blows my mind. And I'm hoping it inspires other Indigenous youth out there.
Awesome. Well, if you're out there watching this and you feel inspired, please share this video to get Corey's mom a little bit more famous. That's sort of like our goal here, right, Corey?
Yeah, definitely.
And there was actually a really nice article in Symmetry Magazine, so we're going to put a link to that in the description of this YouTube here. Definitely read that. Such an amazing story, Corey. Thank you so much for taking time out of your day down there. We did have one final question, about once things are opening up. We're opening up here at the Space Center. You'll be able to come here for visits. But what about tours down there at LIGO? Will people be able to tour down there?
Yeah, we don't have a definite date yet, but we're changing. We're going through different phases of work. And so we're kind of slowly opening up. I don't want to give a date. I mean, it could be later this year, but yeah, that's the hope. Yeah.
Okay. Well, keep an eye on the website. We'll be stay in contact with you. Marley, thank you so much for another Ask an Astronomer. You should know, well, hopefully Marley knows this, but for everyone out there, our next Ask an Astronomer is not going to be in 2 weeks. It's going to be just slightly less than 2 weeks because we're going to have it on June 30th. Corey, do you know the significance of June 30th?
I don't.
It is Asteroid Day. There was an event that happened on June 30th at the turn of the century, a large impact over Tunguska, Siberia, and so that is a day where we think about these big objects that we had a bad day for the dinosaurs. But we're going to have our Ask an Astronomer on that day, so make sure to come right back here on our YouTube channel on June 30th, same time, 2 p.m. Pacific time. And for all of you out there, hope to see you in person soon. Bye for now.
Bye. Thanks, Corey, for coming.